Okay, so I see our next speaker has already shared screen. So in order to keep to time, let's close the discussion of Dimitra and move on to our next speaker, who is Maxime Vassaux.
Hi.
He's a research associate in computational physics, the Center for Computational Sciences in the Chemistry Department, UCL, who's talking about uncertainty quantification, multi-scale simulations of advanced materials. Please go ahead.
So good afternoon, everyone. I'd like to present the work that we are currently doing at the Center of Computational Science in the Chemistry Department at UCL. So we're developing a multi-scale simulation framework where you can compute the properties of what we call advanced materials. So in what I'll show here, just to give a context to what we're doing, are nanocomposites. So the work is done as part of a project called VECMA, whose PI is Peter Coveney, the head of the lab. The purpose of the project is to develop a toolkit, which I'll introduce a little bit later, whose purpose is to enable VVUQ of multi-scale applications. So I'll start by talking a little bit about the applications I'm referring to. So the idea of the application is to if you want to perform engineering a simulation or predictions of the results of engineering tests, such as what we call a compact tension test that you have on the top right here. At some point, you'll need information about the behavior of the material. This information is usually found empirically, running experiments and drawing constitutive relationships between stresses and strain in terms of continuum mechanics that enable to predict, for example, the fracture toughness of such a sample. But as part of our multi-scale application, what we're trying to do is to replace those empirically derived relationships by molecular dynamic simulation. So basically, the workflow looks like this. You have a finite element mesh at the top, which for each of its integration points, so Gauss points, is going to run an ensemble of molecular dynamic simulation. So that starts that build. So for example, at every time step of the finite element workflow, you run. Let's say you have 10,000 cells, 8 quadrature points per cell. You rapidly grow, and let's say you take 5 replicas per quadrature point. However, this is relatively small for an ensemble in molecular dynamics, which typically amount up to 25 or at least 25 molecular dynamics simulation. So you have something which at every time step is going to run for something like 400,000 molecular dynamic simulation. So typically this is already what we could call an exascale application on its own. It scales pretty well theoretically, as all the molecular dynamic simulations you run are completely independent of each other. So you can run them in parallel for every time step. So what we like to do in this project is to actually perform uncertainty quantification on such models. So for right now, we are mostly interested in performing UQ of the inputs of the finite element model. So let's say the geometry of the sample, the temperature of the environment, the load, how the boundary conditions are applied, the load, and so on. So that's where the VECMA project comes in. In this project, basically, so I was mentioning initially, the idea is to build a generic toolkit that's not only specific to, that's not really specific to the multi-scale application I'm presenting right now, but is actually bridging over multiple applications, and among which we have a migration simulation application, fusion, and a climate application, a weather prediction application for climate. So the initial work of this project was to identify uncertainty quantification patterns. So what we call typically intrusive, non-intrusive, and semi-intrusive patterns, and to provide tools that that enable to first, well, generate a UQ campaign. So that's a first tool that we developed and released so far, which is called EasyVVUQ, which enables to generate the samples within a UQ campaign, prepare the encode the input parameter files, and then this is fed to two other tools of the toolkit, which are FabSim and the PilotJob Manager, the QCG client PilotJob Manager, which themselves facilitate the execution of these samples, the simulation of these samples onto supercomputers, which are available in the EU. So typically Supermac in Germany and Eagle in Poland. Yeah. So so in the case of this advanced material applications, the pattern what we call pattern is a CM intrusive pattern. Well, we have an asynchronously cyclic multi-scale application, which means that iteratively you go from the macro scale to the micro scale, and so we call it a semi-intrusive pattern, as we would like to replace the micro scale model by a surrogate, and so we would like to do that online during the execution of the UQ campaign. So at the macro scale, the UQ remains, well, if you only consider the macro scale model, it would just be a non-intrusive UQ campaign where you run a Monte Carlo or quasi-Monte Carlo, or in the present case, stochastic collocation to generate the samples from the distribution of the input parameters. So the main task here was to develop a surrogate model for the molecular dynamics. And well, the issue with the input parameters of molecular dynamics is that they are very, very highly high dimensional. So this is mostly due to the fact that among the input parameters of a molecular dynamics simulation, you have the position of all the atoms in the sample, and that in the current case, so we have something like 40,000 atoms in a simulation, and so their coordinates are, well, high dimensional. Yeah. And then there's a couple of other parameters, typically the temperature, the strain rate, the input strain that is fed by the finite element, and the output stress, which is the results that we would like to predict. So we didn't want to bother too much with building a surrogate that was able to consider all of these inputs. So we actually were able to find a unique state of the molecular system when it comes to mechanics by just considering 3 inputs, which were, well, 3 6-dimensional inputs, which are the current strain, the strain at the previous time step, the past strain, and the stress at the previous time step. So by that I mean, so you have the current strain stress state in the material and the strain that you're going to apply to it. And what you'd like the surrogate to predict is the stress at the current time step, or the updated stress, basically, which reduced a lot the dimension of the inputs. So, well, we tested the surrogate on a simple test case, which is the one I've drawn on the bottom right here. So let's assume you're just cyclically pulling on the system, And so you have a behavior which is, as you're increasing the strain, you have an increase in stress, then you unload the system, so you have a decrease in strain, and then you reload again. So this is a bit wavy because we're only using 5 replicas within for each quadrature point. So the average of the molecular dynamic simulations remain a bit, still a bit, well, fluctuates still a little bit. So we were happy with the, well, I guess the building of the surrogate. So, sorry, I didn't say how we built actually the surrogate, but so since we had only a few inputs, we used a basic artificial neural network to do that. And yeah, that was pretty satisfying. And then, so yeah, just what's coming up next is that so we know that the surrogate model works in the cases where, well, in one of the sample configurations that we've generated the training data on. However, when we're going to try other configurations, other samples which have different input parameters value, we can't actually verify yet how the surrogate is going to behave. So that's where we would like to go next, is to be able to train online the surrogate during the UQ campaign and well, remove the use of the surrogate as we go along during the campaign. And with that, I'd like to conclude. Sorry, I've been quite short in the end with the talk, but so just to summarize, we are currently performing UQ on an advanced material multiscale application used for predicting material properties. Well, we are only done with the surrogate modeling part. We still have to run complete UQ campaigns. In the meantime, we've used a generic toolkit that we've developed as part of the VECMA project. The integration of the development of the surrogate, its training, and hopefully the online learning part during the UQ campaigns will be introduced into another toolkit, another tool of the toolkit, which we call Easy Surrogate, that has just been released last week. And that's pretty much it. Thank you very much for your attention.
Great, thank you, Maxime. That's thanks for keeping to time. We actually have a few minutes for questions if anyone has some, either in the Q&A or people are using the chat as well. So you mentioned using this ANN as a surrogate. You said it was just relatively simple. Can you comment about it a bit? I mean, how many layers, or is it fully connected?
So in the first version we had, it was only one layer of one or two layer. Yeah, since there was only a very small amount of inputs, it worked quite well directly, and the relationship between stress and strains is not extremely linear, so it was trained quite easily.
Okay, thanks very much. I don't think there's going to be any more questions. Yeah, I guess we're going to have time in the panel for talking about the whole set of talks. So we'll move on to the